All right. So far we have learnt about absorption and emission spectroscopy, in the sense that we know that absorbance is epsilon Cl, and absorbance is actually defined as log of I0 by IT, where I0 is the intensity of the incident light, IT is the intensity of the transmitted light. And we also learned that for a non-reflecting absorbing sample, IT is simply I0 minus IABS. Since IABS is the important quantity for us, let me write it like that. We have also studied that for emission spectroscopy, we define something called phi EM, emission quantum yield, which is given by IEM divided by IABS, and a little bit of mathematical manipulation for this expression gave us IEM divided by I0 into 1 minus 10 to the power minus absorbance. And then we said, if we now have an instrument by which we can record absorbance, we have an instrument by which we can record emitted intensity of emitted light, then we should be able to work out the emission quantum yield also. Now, why we want to know emission quantum yield, that will come to later, but let us first see how it is recorded. These are recorded by using instruments that are called spectrophotometers. If you are working with absorption spectrum, it is called an absorption spectrophotometer. If you are working with emission spectrum, then it is called an emission spectrophotometer. Emission spectrophotometers sometimes can be more specialized. Some of them might be such that they allow you to look at fluorescence, they are called fluorimeter, so on and so forth. What is fluorescence? We have not discussed that yet, we will do it later. Okay. Now, let us see what is there inside a typical spectrophotometer. What do you need to do in order, what do we expect from a spectrophotometer? What is the output? As I said in one of the previous modules, the output is this plot, where x axis is energy of or some measure of it, y axis is intensity or some measure of it. So, if you want, say, an absorption spectrum, now we know that here we are going to write absorbance. If we are talking about emission spectrum, in the y axis we are going to write intensity of emission, okay, and then we expect to see a plot that looks maybe something like this. To get this, I should be able to record absorbance in this case, and in the case of emission spectrophotometer, emission intensity at different wavelengths or different energies. Okay. Since most of our discussion will be on electronic spectroscopy, and it is conventional to use either centimeter inverse or more commonly wavelength. I am going to write wavelength for now, but one thing that we should not forget is that wavelength is a reciprocal scale, 1 by lambda is actually energy. So, direction of increase in wavelength is actually direction of decrease in energy, let us not forget that. So, I need to be able to record the intensity of light at different wavelengths. So, how do I do that? What I had drawn earlier is, we have a sample, and right now we are talking about absorption. Some light falls on it, part of the light gets through. Suppose I put some kind of a detector here. Detector in this case is something like an electronic eye. Will we see, what will we see? the detector is going to sense the entire amount of light that falls on it, right, and it will not be wavelength resolved or energy resolved or anything. Okay. It can tell you what is the total intensity. So, in this case, what is total intensity? Total intensity is the area under the curve. Okay. So, it is very easy if you put a detector to tell you what is the area under the curve is. But if you want to know what the curve looks like, then we need to put in something more in between, something that will be able to differentiate colors from one another, something that will be able to differentiate the energies or wavelength of light from one another. Okay. How do you do it? So, we have to use a phenomenon of what is called dispersion, right. We have to break down a polychromatic light, not necessarily white light, but polychromatic light into its component. So, for that we have to use some kind of a dispersing element. Has anybody seen any dispersing element once again outside the lab? Yes. So, everybody has seen a rainbow, and the reason why you see it is that you have this droplets of water in the air which serve as a dispersing element. And I think all of us have read of this famous experiment by Newton, when Newton had collimated sunlight and made it fall on a prism, and the sunlight broke down into colors of different, into components of different colors. Okay. So, this is a way of preparing rainbow. So, what we essentially have to do is, from this light we have to prepare a rainbow, and then we have to make different parts of that rainbow fall on the detector at different times, right. So, that is our job. How do you do? You can use a prism. Nobody uses a prism anymore. Why? Because in a prism what happens is the light actually travels through some amount of glass or sodium chloride or whatever it is, and there invariably there is some absorption. So, you lose light, you lose signal. Instead, the dispersing element of choice is a grating. What is a grating? It is some solid object in which you have lines that are parallel to each other at regular intervals. Okay. Has anybody seen a grating outside the lab? CD. It is just that the grooves are circular. That is why if you look at the shiny surface of the CD, you can see a rainbow. And the principle on which this grating works is that it is called what? Bragg's law. What is it? N lambda equal to 2d sin theta. So, what it essentially says is that different wavelengths travel in different directions. So, polychromatic light falling on this, lambda 1 will go in this direction, lambda 2 will go in this direction. Okay. And what is d? D is the spacing between the grooves, right. So, you have created a rainbow. Now, what happens? One option is I take my detector here and here and here, that is not so easy. So, what is usually done is, first of all you put in a slit. What is a slit? A slit is like two solid plates with a very narrow opening between them. So, if I use a slit here, so the way I have drawn it here is that these are solid plates. So, no light will go through them, but there is a gap between. So, whatever light is here will go through, and you can understand that this light that goes through will have some particular wavelength. Of course, it will be some lambda n plus minus delta lambda. Okay. So, now if I do something, I put a slit, I have a grating, and I put the grating on a revolving something, revolving bench. So, when the grating is in this position, some wavelength lambda n goes through. If I turn the grating like this, then some other wavelength will go through. So, this way I can select which color goes through the slit, and I do not have to move my detector, the detector can sit nicely here. Okay. So, this is a dispersing element and a slit. The combination is called a monochromator. We do not wish to go into more detail of this in this series of lectures. Once again, whoever is interested, please go through our lecture series on spectroscopy. There we have spoken in a little more detail about this, and if you want to know more, I would suggest that you read the book by Skoog. It is about chemical instrumentation. It is Skoog and somebody, but I have forgotten the second name. Skoog is usually enough to find the book, right. So, you need a monochromator. Okay. So, let us clean up this a little bit. So, what did we say? We have light, we have sample, and maybe I will put the monochromator here. I want monochromator, I want light of a particular wavelength to go through, some lambda, lambda 1. So, here I can put in a monochromator. Since I am making a mess of writing, I will just write mono lambda. Okay. And of course, the lamp is somewhere here. The lamp is the source of light. And remember, we are talking about absorption spectrophotometer here. And here we put a detector. If this is the sample, then this detector gives you an idea of what? I0 or IT or what? Intensity of the light that hits this detector. Is it transmitted light or incident light or reflected light or what? Transmitted light, right. So, this detector gives you IT, but I need I0 as well. So, the most common, there are two ways of doing it. First is do the measurement twice, have a sample and do not have a sample. So, spectrophotometers that work in that way are called single beam spectrophotometers, but split beam spectrophotometer is much more common, or sometimes what is called a dual beam spectrophotometer. What you do is you put in a beam splitter. You can think of beam splitter as a partially reflecting mirror. Typically, in absorption spectrophotometers, you want to use a mirror with 50% reflectivity. 50% of light goes through, 50% is reflected, and here nothing is absorbed. So, here what will happen is I0 will be IT in this direction plus IR, I reflected, but that IT will actually be I0 for this. So, it goes here, and then you have a completely reflecting mirror. From there, you put in a reference. What is the reference? Suppose you are doing the experiment in solution phase, there is some solvent. It is usual that you put in that same solvent in the reference side. So, light goes through, there is another detector here, and that gives me an idea of I0. Okay. And then all instruments are run by computer, and computer is good at doing math. So, this gives you, the computer gives you A equal to log of I0 by IT. Okay. Now, if we go back to the previous diagram, see you have a grating and you have a slit, right. What happens if you open the slit? More light gets through, so intensity is higher. But what do you compromise on in that case? Resolution, definitely, right. So, in a typical absorption spectrophotometer, you do not really care about the intensity that is going through, because in any case you are going to take a ratio. So, you want to measure, you want to record a small slit width. So, the delta lambda I was talking about, the width of wavelength, the range of wavelength that gets through, that is typically called bandwidth. The most usual value for an absorption spectrophotometer of bandwidth is 2 nanometer, but sometimes you might need more accuracy. So, some spectrophotometers have variable bandwidth, can go from 0.5 nanometer to higher. Okay. That is one thing. The second thing is, what is the lamp here? Again, I will not go into detail because these lectures already exist in that spectroscopy course, but let me just say that for electronic spectroscopy UV visible range, you use a combination of lamps, deuterium lamp and tungsten lamp. Deuterium gives you ultraviolet, tungsten gives you visible. In some spectrophotometers, they also use xenon lamp, but it is not very popular because first of all, xenon lamp is more costly, more intense, and in absorbance kind of experiment you do not want an intense lamp, because what you are recording is a difference, right. If it is too intense, the difference will not be too much. So, deuterium and tungsten combination is the most popular choice for absorption spectrophotometer. Now, let us move over and talk about an emission spectrophotometer. In emission spectrophotometer, remember, let me draw two spectra together. Let us say x axis is lambda, let us say this is the absorption spectrum, and let us say this is the emission spectrum. Emission typically occurs at lower energy than absorption, for reason is not very difficult to understand. Now, the thing is, in order to get emission, remember I will draw that first diagram that I drew. You are exciting somewhere and then emission takes place. And especially for electronic levels, it is not this simple, you have associated vibrational levels and all that. Emission always takes place from the lowest vibrational level. So, the question is, why do I excite? I might want to excite here, I might want to excite here, and for different samples, different molecules, I might need different excitation wavelengths. So, in an emission spectrophotometer, instead of one monochromator, there are two. First of all, you have this light source, and the light source for UV visible range is typically xenon lamp. When we go to the lab, we will actually show you what a xenon lamp looks like, but xenon lamp gives you white light. In fact, you have actually seen xenon lamp on the road maybe. Sometimes you see these cars with very bright headlight. So, those are expensive cars that are fitted with xenon lamp headlights. So, it is very bright. Regular headlights in car are all tungsten lamps, they are not so bright, bright but not so bright. So, usually use xenon lamp for two reasons. First of all, the output spectrum of xenon goes from ultraviolet to IR. So, huge width, so you can get whatever wavelength you want. Secondly, it is a source of intense light. Okay. Now, unlike absorption spectroscopy, when you do emission, you want an intense source of light. Why? Remember, IEM is equal to phi EM, emission quantum yield, multiplied by IABS. And IABS, what is IABS? I0 into 1 minus 10 to the power minus absorbance, right. So, how much is the absorbance depends on the sample, but the other control you have is I0. If you use a more intense source in emission, it is actually beneficial, because I0 is more and consequently intensity of emission light is also more. That is why xenon is a source of choice for emission spectrophotometer in UV visible range, but then it gives you white light. So, you have to break it down into its components. So, you have to use a monochromator here. What is a monochromator? Monochromator is a combination of a dispersing element and slits. Next, you have the sample and the sample emits. If you are talking about spontaneous emission, then emission is in all directions, like what you see in this light. So, you can in principle collect in any direction, but it is most usual to collect at 90 degrees, unless there is some problem in doing that for some reason. Typically you want to correct at 90 degrees. Why? Because in addition to the emission, you also have transmitted light, right. So, if you put your detector here, then there is a very strong chance that your spectrum will be contaminated by transmitted light. Of course, you will use a monochromator, but monochromators also have their own limitations. So, that problem is usually avoided by recording at 90 degrees. So, at 90 degrees you have another monochromator and then you put a detector. Again, when we come to the lab, we will show you one detector. The kind of discussion we are doing in UV visible range, the detector of choice is photomultiplier tube. You can have more expensive detectors, you can have multiplex detectors, you can have diode arrays, but this is the most usual thing. We will actually show you an example of multiplex detector as well. Okay. Now, in absorption as well as emission, how is the measurement done? We said that we have some kind of light falling on the monochromator and the output is some particular wavelength lambda n. But then you want your lambda n to go from here to here or from here to here. You want to span a range. How do you do that? We said that by changing the grating, turning the grating. So, here now if you think of this spectrum, the spectrum in this arrangement does not come all at the same time. It is built point by point, right. So, you turn the grating at a particular angle, while the grating is moving, no measurement is done, then it stops, then you make a measurement, right. Now, for how long does the grating have to stop? For how long do you have to make measurement at every point? That depends on what kind of intensity you are dealing with. If the intensity is large, then perhaps it is enough if you spend say 1/10 of a second per point. But if intensity is low, then it is essential that you spend more time, because for the time that the detector gathers signal, computer averaging goes on, right. So, suppose you record the signal for some 10 seconds, this is the signal that you get. You record the signal for the next 10, well 1/10 of a second, this is the signal you get. So, there will always be a fluctuation, and the point that you get here is actually the average of all these points that are there. Now, if you spend 1 second instead of 1/10 second for collecting this ensemble of points and averaging, then as we know in statistics, larger the sample size, the better it is. So, if you have a greater integration time or greater residence time at every point, then you actually get a better spectrum. If you spend lesser time, you get a more what is called noisy spectrum. So, there you have to use your judgment. There is no golden rule. You have to look at your spectrum, maybe run it using a small integration time, see whether you get a good spectrum or a bad spectrum, and then increase your acquisition time accordingly, or decrease if the spectrum is too good, you do not need such a good spectrum. But it is important that when you record a spectrum, it should be noise free. Nobody likes to see a spectrum that looks like this. Stubbles may be fashionable, but spectrum with stubble is not cool. You want your spectrum to be absolutely clean shaven, and for that you have to decide what is the minimum amount of acquisition time you need. Okay. There is no golden rule, you have to think on your feet and decide on the spot how much time every measurement is required. Okay. There is another kind of measurement that one can do, and am saying this only because we will show you an example of this. Let us say you have this grating, polychromatic light has fallen on it and it has been broken up into different components. In the discussion we have had so far, we said we put a slit and at a time only one wavelength will go up and we will have one detector. But now it is possible to have not one, but hundreds of detectors. So, each point here is a detector, okay? And you are actually familiar with this also. Your cell phone camera is basically made up of a detector like this. It's more complicated. Here I have drawn a one dimensional array of detectors. Your cell phone camera has a two dimensional array, right. So, if you have something like this, then you can actually get the spectrum in one shot. Then you do not have to do it point by point. But even then, do not forget that what has happened is that the entire spectrum has come at one time, because this every detector has actually recorded something. There also acquisition time is important. There also, even though everything is recorded at the same time, the spectrum will be noisy if your acquisition time is not enough. In fact, in the example that we are going to show you, we do get a noisy spectrum because we do not need an accurate measurement there. So, it does not matter whether you use a point detector or an array detector. It is important to decide what kind of acquisition time, what kind of integration time you require to get a good spectrum. We stop on this note. There is something else that we want to talk about in terms of excitation spectrum, but that can wait. We can talk about it when we actually come to a problem, but let us stop here today. Next day we are going to actually show you the instruments in the lab, and then maybe we will even get an opportunity to talk about excitation spectrum.